All right, let's get started. Welcome to the session on functional programming, technical reasons to adapt. My name is Venkat Subramaniam. We're going to talk about some of the reasons why we should change the way we are going to program. Almost in any mainstream language, well, most mainstream languages now start supporting functional style programming. So what are some of the reasons why we should change the way? We've been doing it in a certain way for several decades. Why should we change it? Well, there are several good reasons, and we'll try to get into some of those reasons along the way. Well, the very first thing is, why should we really think about programming in functional style? Well, the very first reason is, we have seen enormous growth in computer applications. If you've been around for quite a while now, you would probably have noticed that companies have gone from making software available to their employees to making software available for their customers. This is a huge difference in terms of magnitude of scale. I remember going into a bank to perform transactions. I haven't stepped into a bank in a very long time because I can directly access the bank through their software rather than through their employees. So we have a huge growth in computer applications over the past about 10, 15 years, and that's kind of crept up on us. The second problem we deal with is, for most part, what we do, unfortunately, is every single day we are dealing with complexity. That's what we do every single day going to work. We deal with complexity. Now, there are two kinds of complexities we often have to deal with. One is the inherent complexity, and the other one is the accidental complexity. Inherent complexity is the complexity that comes from the problem domain and the nature of the application, and we can't really get rid of inherent complexity. But thankfully, though, the inherent complexity is far less compared to the accidental complexity. Accidental complexity is usually complexity that's introduced by the solution space. So whatever solution we use oftentimes starts introducing complexity. And what do you normally do to deal with that accidental complexity that comes from the solution? Well, you typically find another set of solution to solve it, which in turn brings its own set of accidental complexity, and then it becomes a vicious cycle for us to deal with this complexity. It becomes a huge burden for us to deal with. So if there's a way for us to remove accidental complexity from our code, we can already solve problems in a much effective way. But we also have been programming with object-oriented style, and object-oriented style is extremely valuable. There's absolutely no doubt at all. However, unfortunately, the object-oriented programming doesn't quite deal with the mutable state or shared mutability as well, and that becomes a problem for us to deal with, and it becomes really messy. And that normally comes from the mutable state, but we'll talk about what that is in just a few minutes. And of course, with the emergence of multi-core processors, we are able to provide applications which are more responsive, but the short thing to think about is the world around us has changed. The hardware platform has changed. People are running around with multiple devices now, and every single one of us carry multiple devices, right? If you think about it, you got your computers, you got your cell phones, some of us carrying multiple cell phones, smartphones. We also have other wearable devices, and with all these devices being internet enabled, this is going to only get even more worse as we move forward. And what happens when we are dealing with all these frequent access, big data? Well, so the world around us has entirely changed how we really changed our programming model to keep up with it. And it turns out that the imperative style of programming simply is not adequate. It simply doesn't cut it for us to be able to handle that kind of complexity. So what can we do about it? Well, let's think about a few problems that really haunt us. The very first problem is mutable state. Now, mutability is, let's think about mutability for a minute. If you have programmed in Java, you have programmed with mutability. That is the style of programming in Java. So if you go to a Java programmer and say mutability is wrong, you're not going to get much love from them, right? So we do mutability all the time. So mutability is okay. What about sharing? Well, sharing is a really good thing. Remember what mom told us, right? Mom tells us share, so mom is always right. So absolutely sharing is good. So mutability is okay, sharing is good, but shared mutability is devil's work. And the minute you bring in shared mutability, all kinds of problems creep in. And we really find it hard to deal with shared mutability. So one of the very first things in functional programming is to eliminate mutability as much as we can. And that is one of the very first things. But why is really mutability such a really bad idea? One of the reasons is the code is very error-prone when you deal with mutability. Now, you have probably dealt with this quite a bit already. When you're dealing with the program, when you have mutability in it, it becomes really hard to work with the program, and usually bugs creep in. I had a programmer come to me one day and he said, here's a function I've written, it doesn't work, can you please help me? Well, this was his code. I don't know anything about it. I look at it. It was not really that long at all, about 30 lines of code, so it's not really that bad. But I'm looking through the code quickly, and I tell him, if you send this input, it should produce this output. He says, yeah, I know, right? But it doesn't. So we both are looking at the code like we are idiots for several minutes, and then suddenly I noticed on line number 7, he actually is modifying the input parameter given. And I asked him, did you really mean to change this input parameter here? And he gets up and says, I'm stupid, and walks away. And so we don't even think that we would be modifying variables sometimes, and it causes confusion. Now, if you really think about this, this has been a problem for a while, and there are solutions being suggested to fix this problem. For example, let's say you have a Java code for a minute, and in this Java code, let's keep it really simple, let's say foo, and I have int a in here, and maybe I have a number of lines of code that say the code is sitting here. And right in the middle of this code, I'm going to say a equals 2, and I'm just changing that particular variable. Of course, when I call foo with the value of 4 in this particular case, you can see the compiler did not give us any error. In fact, it just let us run through. It said OK, but we know this is not OK. Well, why is this not OK? Well, if you modify variables arbitrarily, it can become really error-prone. Well, there is something that effective Java has told us. What does effective Java tell us? Effective Java says, do not pass a variable like this. Instead, do a final. Well, why do we put a final in this case? Well, in this case, of course, the compiler immediately gives you an error saying, on line number 8, it says, sorry, you cannot modify the input. So effective Java says, as much as possible, make your variables immutable, and there's a reason they say it, because the code becomes more error-prone when you have it. In fact, you can go to the next extent. If you look at this code right here, if I say define foo, and I say a is an integer, and of course, within this function, I'm going to say, here is the variable a. I call foo with a 4. This is Scala code. But what I'm going to do within Scala here is, I'm going to say a equals, let's say, 2, much like I did in Java. And when I run this code, notice it says, you've got to be kidding me. It does not allow me to modify the variable because it says an input parameter should not be modified. Don't do that. Now, I've had people come to me and say, well, that's interesting, I'm glad Scala does that, but is there a setting where I can change that so I can actually modify it? And the answer is yes, you can go back and program in Java for that, right? So the point really is, the language is very highly opinionated. It says, no, you shouldn't do this because it's the wrong thing to do. So in the case of Java, you have to put final, but that's the implicit behavior here in Scala, for example. And why do we do that? Because when a variable is mutable, it becomes error-prone. And more mutability you have in code, the more error-prone the code becomes. So here is a way to think about it. How many people in this room can juggle? Only a few hands went up. And for the people who raised the hand that they can juggle, how long can you juggle? Half hour? No? 1 minute? 2 minutes? And while you're juggling for that minute, what else can you do? Pretty much nothing else. In other words, you're saying, when you're juggling, your life is wasted, right? Because you cannot do anything else while you're juggling. Well, actually, that's not true. Everybody in this room juggles every single day. That's called programming in Java, right? You do this when you go to work because you create mutable variables, and then what are you juggling? You're juggling all these in your mind. It's very frustrating, but yet we do it. It's a lot of fun, isn't it? So we keep doing this over and over, but that's like our equivalent to juggling. We do this quite often. But thinking about this, it becomes extremely hard to maintain code when these code become mutable. In fact, certain languages take us in this right direction. So for example, in Scala, I'm going to say val, and I'm going to say x equals 4, and I'm printing the variable, whatever the value is. It says it is 4. But if I say x equals 22 and print the variable x, notice you get an error right away. On line number 5, it says you cannot modify the variable x because it is immutable. So languages can be written to favor immutability. Well, of course, Scala being a hybrid language, it does have a little loophole. You can declare this as a var, and then, of course, notice you can actually mutate it. Well, what is var? Var is called the keyword of shame in Scala. So anytime you use var, you cannot make eye contact with your colleagues. You look down on the floor and walk, and they know you have done something really bad, and they'll come back to help you refactor the code. So it's very easy to identify when you have mutability in code, unlike Java where you have to put more pain to find out what has been immutable versus mutable. The language kind of makes it a lot easier to detect immutability versus mutability from the get-go. So that is something you can do quite effectively because mutability causes more errors. The code becomes really hard to reason. How many times have you written a code where the function does a lot of mutability and you simply cannot really figure out what the code is doing? And I'm sure you have done this at some point in time, right? You're looking at this function and you have had it, so you take a piece of paper, you draw a little column, and you start putting variable names, and you're jotting down the values as they change. And remember doing that? And then this all goes very well until somebody interrupts you, and you lost the whole thing and you got to start over. That's called lowest point in programming because we cannot really keep all that in our head with all the mutability that's going on. So reasoning code becomes extremely hard when that happens. If somebody tells you, here's a code that's doing a lot of mutability, now make this code concurrent, that's going to be really problematic because when a code deals with shared mutability, it's extremely hard to make the code concurrent. It becomes almost impossible. So that's another reason why mutating variables is such a bad idea. But having said that, what does functional programming say? Well, functional programming has some really interesting recommendations for us to avoid a lot of these accidental complexity. So a way to think about this is functional programming is a way to minimize accidental complexity. That's a really nice way to think about it because what we deal with quite often in our life is accidental complexity, so we could first of all start thinking about it. So functional programming is a way to deal with or minimize, let's say, is a way to minimize, if you really think about it, and minimize what? Well, accidental complexity. So accidental complexity, and that's basically what you're trying to do every single day is we are dealing with the complexity that we have to deal with all the time, and that's basically the idea. So FP is a really good way to deal with or at least minimize the accidental complexity quite often. So given this, what can we do? How do we minimize these things? But before we talk about it, let's think about where these things have come from. So here's a quick question for you. What year, don't worry about being right or wrong, I'm wrong most of the time, what year do you think object-oriented programming became mainstream? Like nobody ever even questioned they started writing object-oriented code. Do you remember the year? What was it? Yeah, well, 1990, give or take, right? So 1990, that's great. Do you remember the year object-oriented programming was introduced? Yeah, 1967. Can you imagine this? 1967 to 1990. What was that? 23 years. If OOP was a human, it had a neglected childhood. Nobody really cared about it. Until when it was 23, it's like, hey, handsome, do you want to hang out, right? So that was a very long time. Okay, what year do you think functional programming concepts was introduced? Not quite functional programming itself, but the underpinnings, the concepts behind, the mathematical concept behind it. Any guess? Well, 1929. Well, everybody here knows of Alan Turing. Well, this was Alan Turing's boss, Alonzo Church. He was a professor for Alan Turing, and he introduced the concept of lambda calculus and a lot of these underpinnings. What year do you think functional programming became mainstream? Okay, that was a trick question, not yet. Well, 80 years later, we are just about getting excited about functional programming. So when somebody comes to me and says, in the programming world, things change really fast, I ask them, what are you smoking? Right? It's taken so long for us to adopt. We are very slow in the way we really pick up things. So this has been around for quite a long time. But what does it really provide for us? Some really nice recommendations to minimize the accidental complexity. And one of them really is that what is old is new again. It's been around for a long time. And it says, let's program assignment-less programming. Now you say, wait a second, assignment-less programming, How in the world could you possibly program with no assignments? Well, we talked about the reasons why you want to program with no assignments. The code becomes easy to reason, easy to understand. It becomes easy to debug. It becomes easy to work with it. It has fewer errors. You can make concurrency much more. I can give all these reasons why we don't want to do assignment. But how do we possibly program with no assignments? Is it even practical? Let's think about something else a little bit different. Step back for a minute. We had procedural programming once upon a time, and then, of course, we then started doing structural programming. What's the difference between procedural versus structural? Well, one of the differences is, good old Dijkstra said, we should not use goto. In fact, he wrote this phenomenal paper where he said gotos are evil, and we should not use goto. Now, if anybody even thinks of using goto, Dijkstra moves in his grave, and we don't want to be programming with gotos. However, when we say we are not going to program with goto, does it mean we are not going to ever use goto? I want you to entertain this thought for a second, just a little bit. Now, suppose I go to Java over here, and in Java, I'm going to say blah, and I'm going to put a little semicolon and run it, and notice the error very carefully. The error message here is, blah is not a statement. Just keep that in mind. Blah is not a statement. Now I'm going to change this to goto with the semicolon. When I run this code, notice what Java says. It says illegal start of expression. It did not say it's wrong to use it. It says you're using it in the wrong place. Now, why is that? Well, actually, goto is a keyword in Java, but they tell you, I dare you to use it. So they don't want you to use the keyword goto. That's how angry they are in you even ever attempting to use it. They don't even want to use it as a variable in your code ever. Well, that's basically what the goto is treated as. However, if you remove that for a second and do something extremely simple for int I equal to 0, I less than, let's say, 10i plus plus, and then within this, I'm going to simply say if I is greater than 5, I want to simply output the variable I. Well, sure, that was a very simple code. However, when I go to the command prompt here, I'm going to say Java P, and I've already set up -e as the option on my machine. So if I say Java P and take a look at the class it generated, well, sure enough, that we're looking at the bytecode equivalent of what's being developed. But if you focus really quickly here, guess what that code actually has? It has a goto under the hood. You're like, wait a minute, we're agreed we're not going to use goto, but how come there is goto over there? Well, it's very simple. You and I don't use goto. Much like you don't go to children at home and say, hey child, I'm going to go take a shower. In the meantime, entertain yourself with this pair of matches, right? You don't give matchsticks to children and walk away. I hope you don't. So the similar way, but that doesn't mean you don't have matches at home. Well, there are matches at home, and guess who uses it? The adults do. That's exactly the point. So they are saying, you guys don't get to use goto, but we adults can use goto under the hood. I'm quite happy with it, right? I would rather program in a way that the code is maintainable rather than have to deal with it. So the point I'm making is, in structured programming, we don't use goto. It doesn't mean there is no goto ever. We don't use goto in our code, but goto happens under the hood in a very controlled manner. In a similar way, in functional programming, we don't use assignment. That doesn't mean there's no assignment at all. It simply means there is assignment under the hood. Now you may say, aha, wait a minute. If I don't do assignment, and if they do assignment, is that really assignmentless programming? Well, for all practical purposes, I would argue it is. And the reason is, if you do assignment, what happens? Well, concurrency is your problem if you do assignment. Debugging is your problem. Understanding the code is your problem. Maintaining it is your problem. Reasoning it becomes your problem. Errors become your problem. If they do assignment, all of those things are their problem. In life, you always make things other people's problem, right? So that is definitely much better. So as a result, yes, they do assignment, but let them deal with those issues. I don't have to deal with it at my level, and as a result, it becomes a lot more easier to maintain the code, and that is something you can move towards, and don't have to really be stressed out about these particular problems. That becomes a lot better, easier to work with. So given that, I'm going to say in this particular context that we can think about it this way. We can say that a go-to is to structural programming, so structural programming as to, let's say in this case, as assignment, right, is to functional programming. So the way to think about this is, much like how you don't want go-tos in a structural program, you don't want your assignments to be available in functional programming. That's an interesting way to think about it, to say that's kind of the equivalent of what the real philosophy of this is. So go-to is to structured programming as assignment is to functional programming, program with no assignments. Well, okay, we can program with no assignments, but what does that really mean? Well, it leads to immutable state. So what does it mean to program with immutable state? Well, rather than taking an object and mutating the object, what we try to do is we say, I'm going to transform the state of the object rather than mutate it. So in a very similar way, if you think about it, I could take a bill and I could say, could you do me a favor? I want some change. Could you break this bill? Well, if I give it to him and say, could you please break the bill? I'd be really upset if he says, sure, and tears the bill into two and gives it back to me. I didn't mean him to break the bill by tearing it apart. What I expected is for the bill to disappear in his pocket and maybe some smaller amount of denomination of bill to come out. So you're transforming rather than mutating. In fact, almost any government would like for the bills to be immutable. You don't go around and say, well, I guess I can start devaluing these myself. That's a way to go to jail, right? So there's no really interest in mutating stuff like that. In a way, if you really think about it, you're going through state transformations rather than state mutations. And that's one of the biggest things we try to do in functional programming is encourage more of a state transformation. And of course, functions are created as a first-class citizen. And what that means is we are going to be programming with the so-called higher-order functions. So what are higher-order functions? Well, when you deal with programs, we normally pass an object to a function. You can create objects within functions. You can also return objects from functions as well. So typically when we write code, we do things like this. So for example, we could do things like you can have a function that you're creating. So we could say, for example, public, and then I could say my function is foo. And you could send some object, my class, you can say instance, and you can pass the instance to this particular function. You can certainly do that. Well, also, so when you call foo, you would normally say foo, and you could call the instance and pass the instance to it. You can also say my class, for example, and then another equals, and then you can create this other object. So another equals new my class, and you can create an object within a function. You could also say return another, and you can return an instance from this particular object as well. Well, you are able to pass objects, create objects, return objects. Well, in the case of functional style of programming, we can think about this as, let's say, F1, and we can pass to this particular function not just an object, we could actually pass functions. So for example, in this case, I'm going to send a lambda where this lambda is going to do some work, whatever that is. So in this case, if you notice, what we are passing to this function f1 is a lambda expression. A lambda is nothing but an anonymous function. So that makes f1 a higher order function compared to the function foo, which is a normal method or a function. So a higher order function can receive a function as a parameter. Not only can you do that, within the function f1, you can also create another function. So in this case, I could say some operation, and I can create a particular code where I can say this is going to be an operation I want to perform. I can create a function within another function. So we can say func equals, and I can set that, whatever the type is. But once I do that, I can also say return, and I can return the function as well from this particular function. So unlike foo, which can receive an object, create an object, and return an object, well, the function f1 can receive a function, as you can see on line 19. It can create a function. It can also return a function as well. And that makes the f1 a higher order function. And that's basically the idea behind higher order functions, is that you can work with these kinds of functions. But more so, in functional programming, functions do not have a side effect. So what does it mean a function doesn't have a side effect? What that means really is you can think of a function as a little cylinder. You send some data as an input, and it gives you an output as a result, but nothing ever changes while the function is running. So a pure function, or a function with no side effect, simply means while that function is running, it doesn't go modify a global state. While the function is running, it doesn't really depend on a state that's changing. So that's basically what a pure function is. What are some of the benefits of using a pure function? Well, there are some really good benefits of using a pure function. Well, the very first benefit is it gives you an enormous amount of consistency when dealing with a pure function. So, for example, I worked on a project years ago when we simply transported the code. It was C++ code. We transported the code from one version of compiler to another. We just ported the code over. Well, we didn't make any change to the code. The code was exactly the same. We just compiled it using two different compilers. Well, one of the programmers noticed that there was an error in one of the 7th or 8th decimal place in the code, and that was a little error. We were trying to struggle to find out what it was, why it was, and this guy took several days to figure this out. And one morning, he's gone home in a few days trying to figure this out. One morning when we come to work, he was waiting there with Beyond Stroop C++ open with a paragraph highlighted. So as we walked in, he said, "Come on over, I want to show you this." And he shows the code we had in the application, and the code looked something like this. It was something along the lines of A plus B plus A plus plus plus, and then there was more to it. Well, clearly notice that variable A is being mutated right there. You're modifying in this particular expression. So he shows this code and then points to the paragraph in Bjorn Stoster's book, and in that paragraph he clearly says, "Don't do that." And he said, "I want to know which moron wrote that code because I'm going to kill him now." That's what he said. He was so angry. But what was wrong in this code? Well, the problem in this code is right in the middle of this expression, the code is modifying a state, and the ANSI C standard says, "Tough luck, I won't tell you how the compiler will deal with it." And so one compiler decided to do it in one order, another compiler decided to do it in another order, and that resulted in the error in the code. That's an example of a code that causes real big pain, and debugging this becomes a nightmare, and so this can be really problematic. But there are some really good things we can do by keeping functions pure. So let's look at one example of a pure function here. Let's say A plus B is a function we are interested in. Well, clearly that's a very pure function. There's nothing really difficult about it. But let's think of an example of what we're going to do here. Let's say we're going to pass the variable values to this particular function. I'm going to pass a variable value of 2 for A, and I'm going to pass a value of 5 for B, let's say. Well, what's going to happen in this particular example? So if I can ask you to volunteer, will you be kind enough to volunteer for me? Will you volunteer with the help? Can you help me? All right, so here's the question for you. Tough math problem. What is 2 plus 5? 7. He said 7. That's awesome. He knows his math. Now, I'm going to ask him one more time. What is 2 plus 5? Yeah, 2 plus 5. So it doesn't matter how many times I ask you. You're going to keep saying the same thing, aren't you? Why is that? Because he knows that plus is a pure function, isn't it? So it doesn't matter how many times. We could be here for an entire day, right? What is 2 plus 5? He's going to show 7. He's going to be extremely consistent. So the problem here is, well, the nice thing about this is, no matter how many times we ask, the output is going to be exactly the same. 2 plus 5 is 7 all the time. So there's no difference at all whatsoever. Well, the reason for that is it's a pure function. So what happens when a function is pure? As long as the input is exactly the same, the output will be exactly the same. So what does that mean? Testing such a function is extremely easy compared to testing a function where things constantly change. So from the testability point of view, a pure function is easier to test. A good design will need fewer tests. That is one good thing about software design in general we should keep in mind. So we are all trying to write tests, but a good design needs fewer tests. And that is something we can work really hard to get to the point where a good design can have fewer tests. Well, functional code is a better design. It doesn't have mutability. And as a result, we need fewer tests for it because it doesn't change a whole lot. But on the other hand, let's say for a minute I'm going to change my question to him. If I were to ask him how much more time there is for this talk to be over, his first response is going to be, feels like it's too long. Well, then he's going to say, well, there's 30 more minutes for the talk to be over. But if I wait for 5 minutes and ask him how much time is there for the talk to be over, he's probably going to tell me 25 minutes and not 30 minutes. Now, why is he suddenly inconsistent? Why are you not consistent anymore? Well, the reason is he is depending on something, an external variable, which is the time. And so as time goes on, the type keeps changing. Now, this becomes really hard because when I ask him how much time there is more for the talk to be over, while he's trying to answer, let's say his colleague next to him interrupts him. And he tries to answer him and comes back and answers me, well, we are in trouble because he's going to be really not giving the consistent result. I could see what the time is, but the reply from him is not going to be the same because there's been an extra delay in him responding. So this can become really annoying when you work with code for testability purposes. So to give you an example of this, I took a very long flight. It was about 24 plus hours flight. And when I finished my journey, I landed in this wonderful city. I checked into the hotel. It was 2 a.m. So what's the most logical thing to do after a very long flight and it's 2 a.m. In the middle of the night? I decided I'm going to go edit my code. So I took my code, and I have this habit of making sure I run all the tests before I touch the code. Well, in this particular project, I'm the only developer, so it's all my code, and I had written this code a couple of weeks before. I haven't touched it since. So I said I'm going to make a change to it. So I took the code, and the very first thing I did was I ran all my tests. And to my shock, a few of my tests actually failed. And my first panic was, what do airlines do to code these days when you travel? Well, then I looked at the tests that were failing, and I was quite surprised what actually failed. I had a few tests where I'm starting a task 3 hours earlier, and I'm asking if the task is completed on the same day. Well, guess what? At 2 a.m., the task you start 3 hours earlier is not ending on the same day, it's ending on the next day. Well, this is a bit of a good news. This tells you I never work at 2 a.m. when I'm home. So it's basically that I was just trying to run this code. But I learned my lesson. What the problem here was, the problem is my code is actually pulling the time information, and that makes the code very unpredictable. So I refactored the code in a way that the time is actually passed in as a value. Then it goes and queries the time as a variable. Then, of course, in my test, I say, now if the current time were this, and if the current time was that, how much did the task finish at the same time? So, for example, I can ask him, if the current time is 1 p.m., if the talk is supposed to be over at 1:30, then how much time is left? No matter when I ask him and how many times I ask him, his response will always be 30 minutes. So in other words, you remove the variability out, and you can pass them as constants. So one big benefit you get is the code is easier to understand, easier to maintain, and the code also becomes easier to test with the purity of functions. But there is more you can do with it actually moving forward. Let's change the problem just a little bit. So are you ready for your next math challenge? All right, he's all up and ready. So I'm going to ask you this question. What is 123 plus 85? And say it louder so I can hear you. You want to call a lifeline? What is it? 210. Well, it should be 5 plus 3 is 8. And then 8 plus 2 is, so 208. Okay? Is it correct? Can somebody verify? Okay? So we got the result. Well, let's try this one more time. Are you ready? What is 123 plus 85? What is 123 plus 85? 208? All right, let's try again. What is 123 plus 85? Did you notice a difference? Was there any difference at all? He is wicked fast now than he was the first time. How the hell did you do that? Does anybody know how he did it? He cached it. Does everybody here understand the word caching? Yes, you do. in computer science, you never use words everybody understands. Why? Because it is not cool. So you call it memoization. What the heck is that? That's awesome. So yes, it is caching, but it is called memoization because nobody understands what that word is. But he basically memoized it. Isn't that awesome? Because he's extremely smart, as a human being is. He is extremely error-prone. Sorry, you are a human too. That's why he double-checked it. That's why he called for help from other people. But once he got it, what did he do? He memoized it. And he said, this is cool. But what really made him memorize? There's something else he knew before he could memorize it. What is it? That's correct. That function is pure. If the function was not pure, he would definitely not memorize it. And every single time I ask him, he would say, gosh, I got to do this work all again. So what if a function is pure? If a function is pure, a language has the liberty to memorize calls. And how cool that is when memorization can happen. You cannot imagine memorizing if you don't have purity of functions. Because every time you call with the same input, you want to be able to get the same exact output. And that basically is memoization. It is possible because of that property that you get the same output no matter how many times you call with the same input. So purity of functions gives us the ability to memorize. Now, in a language like Haskell, memorization is done much more effectively because language like Haskell has a better way to determine if a function is pure. But in Java-like languages, we have to really take the burden of that. So languages like that can do really good memorization. Of course, in Haskell, they use what are called thunks. Thunks basically are a little code block that can be memorized, and so the next time you call, it says, I've already done this work with this input. I don't have to redo the work. It can give you the result right away. So languages can be built with more efficiency. Not only can you do that, let's think about this a little bit further. Let's say we have a function here. Let's say function f1 is a plus b, not in any particular language syntax. Function 2, let's say, is a minus c. Now, if you really think about it, let's say further down, you're going to use result of f1 and f2. So in this case, of course, let's say the compiler says, I'm going to do function f1 first, and then it says, I'm going to do function f2 next. So this could be an order in which the compiler decides to execute these two functions. Now, clearly, what a good compiler can do is, it can say, oh, I've already evaluated function f1 the last time with this data, so I can replace a call to f1 with the result of the data, so I don't have to redo it. But not only that, a compiler could also go to the extent of saying, I'm going to run the function f1 second, but I'm going to run the function f2 first. In other words, a compiler often has to do these kinds of optimization. Why so? Because a compiler may say, look, I find that these variables are already in my register. Doing this operation before doing the other operation could actually be more effective. And so when it comes to these kinds of functions, a compiler may say, I can replace the call with the value, or I can reorder calls any way I want to, as long as the result is exactly the same. And so this particular thing is called referential transparency. So referential transparency simply means as long as the result of your evaluation is consistent, you can either remove or replace the computation with the result, or you can reorder them as long as the result is exactly the same. So in other words, what a compiler can do at this particular point is, the compiler can say, oh, here you go, here is function f1, and here is function f2. I'm going to run function f1, and then I'm going to run function f2. And the compiler can go through this particular cycle to run these two functions. Just to see that these two are different functions, let's actually see this is a different function. So it could run this in this particular order. Or the compiler says, gosh, I can run function 2 first, then I will run function 1. It can reorder it if it wants to. We look at optimizations like this all the time in compilers. Or even better, if the compiler knows a little bit more, and there's one compiler that knows a lot, which is called the Jit Compiler, and the Jit Compiler says, I'm going to run them concurrently because I have a multi-core processor. So in other words, if this is a computation that deserves parallelization, a compiler can easily reorder or even run them in parallel, and that kind of benefit you get because the functions are pure. If the functions were not pure, if they were performing impure operations, the compiler is going to say, that's a very smelly code, don't even go near it, and it will not be able to do as much optimization. I'm going to give you the world's dumbest example of how optimization can help with purity. So think back about what you did this morning before you came here. I look around the room, and there's a bit of a good news here. Everybody here is decent, which is really nice. They have got their clothes on. That's nice. Now, in the morning, when you started to work, you had to put on your clothes, and you know who you are when I talk about you. You put on your shirt first, and then you put on your pants. You don't have to reveal this to anybody else, but you know who you are, right? You put on your shirt, then you put on your pants. There are also people in this room who did the other way around. They put on their pants first, then they put on their shirt. But here's the good news. Nobody cares, right? Nobody cares. Nobody comes to you and says, oh, you are one of those guys who put on the pants first. Nobody ever knows, right? That is the beauty. And in fact, tomorrow morning, while you're getting dressed up, you can stop for a minute and say, this is excellent. Venkat taught me something yesterday. I've always been putting on my shirt first, but for a change, I'm going to put my pants on first. Have the courage. Be liberated. Nobody would ever know, right? And that is the beauty. You can perform this optimization any way you want to, but nobody would ever have a clue. And that is exactly what compilers do. As long as the result is exactly the same, they can perform any kind of optimization as they want to, and that's basically possible because of the purity of operations. It doesn't matter which way you do, as long as the net result is exactly the same, and that's what basically it gives you. So given this particular feature, you can have enormous amount of compiler optimizations possible. So we looked at a lot of benefits of this. So what does this really mean? Well, we can go from a functional style to a functional programming, but what this really means is you're going through a purity of functions versus higher order functions. In a purely functional language, you got a couple of different things given to you automatically. So I'm going to emphasize in a slightly different way, so let's say in this case, pure functional programming languages means it's going to be equal to purity of functions plus higher order. And I'm going to say functional style on the other hand. So functional style of programming simply is equal to using higher order. So in this case, higher order functions. So in other words, languages like Haskell enforce purity of functions. A language like Java only gives you the ability to do higher order functions. They don't enforce purity of functions. It is for you and me to really start enforcing purity of functions because a language doesn't do it. So when you have a strictly functional language, you got higher order functions and functional purity. In a language like Java, you only have higher order functions. You have to do the extra work of purity yourself. There are hybrid languages like Scala and F#, where the language gives you higher order functions and purity, but they also give a way to violate that with a switch. So that's why they are hybrid languages as well. So there are languages in this spectrum going from one end to the other. But what does it really mean? Rather than mutating data, we are transforming data. So we go through these series of transformations or function composition. So essentially what this means is we're going to be programming from an imperative style to more of a declarative style. That's basically what we are trying to do. So let's understand what this actually means. And I want to draw the distinction between the word declarative, the word functional, and how they relate to each other. So in the case of declarative style, you tell what and not how. In the case of imperative, you say every single detail you want to say. So to understand this, let's look at one example here. Let's say I'm interested in finding if a person or a name exists in a collection. So I'm going to say in this case something like let's say find Nemo. So I'm going to send a bunch of names and ask it to go find Nemo in this particular case. Well, I have written code like this in the past, so let's see how this is going to feel to write this code. So I have a list of, let's say, string, and I'm going to call this as, let's say, names, and I want to know if the name Nemo exists in this collection. So what do you normally do? You say Boolean found equals false, and then you start looping through. So for example, string name comes from, let's say, names, and then you can start looping. Now, what is this called? Well, usually call them as flag variables. Now, flags are the lowest life form in programming. You don't normally give a good variable name for it. You normally call it temp or t, saying that you don't deserve any status in the world, right? So we do that often because these are really variables we don't really like using, but they all end up being there. Then what I can do, of course, in this case is I could say, for example, if name.equals, let's say, Nemo, and I could then say, for example, well, we could simply say, well, we found that, so found is equal to true, and then I could break out of this. Now, given this, of course, how do I go about really determining this? So I could say if found, and we could then print out, let's say, found Nemo. We could say found Nemo. And then, of course, if it did not find it, you could say else, let's say, Nemo not found. So if you run this code, you are really exercising this particular variable. Oh, where's this variable Nemo? We want to bring it. So let's say in this particular case, we got a bunch of names, and I'm going to call this. It says found Nemo. You could also try with a collection where there is no input. But if you really look at this code, this is an imperative style of programming. And so what do you do in imperative? So in imperative, you do a couple of different things. So it's imperative, and in the imperative style, you do say how and what, and then plus you have mutability that you have in place. So in other words, in this particular case, you are telling how to do and what to do, and you're doing all the effort yourself. Let's take a look at how this is going to feel like in a more of a declarative style. So I'm going to say declarative, and what do you do in declarative? You focus on what and not how, and of course, you avoid mutability as well. So in declarative style, you try to minimize mutability or eliminate it as much as you can. Let's look at an example of declarative style for this particular code. Well, that's a lot of code, as you can see right there, but thankfully we don't have to write as much code as we did here. So let's grab just the last part here, and I'm going to say if found, then go ahead and do all of that. But instead of found, I'm going to change it to names.contains, and I'm going to say Nemo, and the code actually still works. But we simply used contains over here. So what does contains really do? What contains does is, it tells you whether the collection contains that name or not. But the question is, how does contains do the job? Well, some of the answers I normally get is, oh, it loops through every value to tell it. And somebody said, oh, it does a binary search. But here's the right answer. I don't care, right? So you need to cede control and say, I don't need to know that stuff right now. Okay, I don't care is a bit rude. You don't want to say I don't care. There's a much better way to say it. It's called encapsulation, right? That sounds a lot better. So it's like it's encapsulated. I don't need to know that stuff. And so as a result, you can change it much more easily. If you do something, you have to put the effort to change it. If you don't do this and let another function do it, it's easy to change that. And that's essentially the idea behind this, is you don't commit to those details. But this particular code is not functional style. This is purely a declarative code. So what does it mean by declarative? In declarative, you convey what you want, and you don't worry about how to really implement it. And that is basically a declarative style. There's nothing functional about this code. On the other hand, we can go a step further from this, and we can say, I want to perform, let's say, double all the even values in a collection. How do you double all the even values in a collection? Well, to do that, what you're going to do here, let's say we have a list of values here, and in this particular case, I have all these 10 numbers. I want to double the values in this particular collection. So you say list integer doubled equals new array list, and you create an array list of all the values to begin with. And then once you create this array list, what do? You say for int element in numbers, and then you're going to say doubled dot add, and you're going to say e times 2. And then, of course, when you're done with it, you can print out all the values that have been doubled. Well, if you look at this particular code, you can see in this case you are doubling the values, but this is an imperative style as well. So this is imperative, and in this case, of course, what and how and mutability going on also. So notice how we are mutating the variable over and over and over in this particular code. That's an example of a very highly mutable code. So that is an example of imperative style. We can change this to more of a functional style this time. So declarative, and I'm going to say functional, and I'll draw the distinction in a minute. So in this case, what I can do is I can simply say output, and I'm going to start with numbers.stream. So think of a stream as a fancy iterator. And then once I take this particular stream, I'm going to say, in this particular case, do a mapping operation where given an element, double the element, and then reduce it in this case. So it's a map reduce. And I'm going to say 0, integer, and I'm applying the sum operation on it and performing the reduction. So if you notice in this case, well, actually, I'm performing only a double, right? So pardon me. I'm going to double the values and store it. So collect is another form of reduce that I want to use here. And I'm going to call it toList method to perform the collection into a list and return a list of value in the very end. So where does the list come from? The list is coming from the import. We're going to import here stream.collectors. And I'm going to bring in the toList method, which is present in there. So in this case, of course, when I run this code, you can see it produces the same result as the other one. But this one is functional and declarative. Now, why is it declarative to begin with? It is declarative because you say what you want the code to do rather than saying how the code should work. So you said, I want you to take this collection, double each of the values, and put it back into a list. You didn't tell how to really iterate through the values. The iteration is left to the underlying library, so you don't have to really waste your effort and time showing how to do the iteration, which means that there are some really good benefits to doing this. For example, let's say you have the code in the top, and somebody comes to you and says, this is great, but this collection is really long, and also the operation of doubling is really slow. Imagine it's not double, but something else. And they tell you to take this code in the bottom, and they ask you to make the code concurrent. What would you say? You would say, where's the nearest exit? I want to leave, right? Because when a code has mutability and shared mutability, making the code concurrent becomes extremely hard and troublesome. However, if you look at the code in the bottom, we had some really nice benefit. Each of these functions you can see is pure. So the function that you see right in the middle is a pure function. It's not mutating any variable. It simply says, my job is to really take this value and return a double of it. I'm not performing any mutation. It's a pure function. When you have pure functions, we have all the benefits we talked about, but one extra benefit you get is that you can make this code a lot more easily concurrent. So in this case, you can simply say, over here, a parallel stream, and you can, of course, get the results much more quickly. If this was taking a lot of time to execute, you can make it very quick by turning it into a parallel stream rather than having to do it sequentially. So that becomes extremely simple to do. Now, of course, this was easy to write, but it was only easy to write because we did the right things, which is we really used pure functions. If you had not used pure functions, if you're mutating stuff, that's the fastest way to fail and get wrong results. So you got to be very careful using these techniques. Purity of function becomes extremely important in the process. But I mentioned that this is actually a declarative unfunctional. But on the other hand, if you notice, the one in the top I said is only declarative and not functional. So in other words, if you were to draw a big circle, think about this big circle as the circle of declarativeness. Within that big circle, draw a small circle. That's functional style. The functional style is contained within the declarative style. So all functional code is declarative, but not all declarative code is functional. So if you notice on the top line, line 21, that is declarative, but it's not functional. You're not using any higher order functions here. It's simply a function, and it's declarative. If you look at the code in the bottom, it is declarative, no doubt, but it is also functional because that's a higher order function you are using. So all functional code, so that's a way to think about it, if you will. You can say all functional code, so in this case, functional code is declarative, but not the other way around, right? So not all declarative code is functional, but all functional code is declarative. So that is basically the way to think about how this can form together for making our lives better. So we saw the two approaches, but what's the difference? In the case of an imperative, you say how to do stuff. In the case of declarative, you focus on what to do and let the system decide how to do it. You decide to use library functions to do it. You are favoring immutability and transform data rather than mutate data between these two styles. You have side effects often in imperative. You avoid side effects. You write pure functions in declarative. You can pass objects, whereas here you can also pass functions around in the declarative, which is the functional style we are talking about. It's very hard to compose generally, but in this case, it's very easy to compose with these also. And that takes us to rethinking the way we would do things. So if I want to find the number, prime numbers in my code, we can go along the lines of imperative style we normally write, but it's time for us to rethink about the way we do things. So in other words, if you're going through a process of doing all work yourself, ask yourselves, are there better methods I could use? And the chances are you're going to find a few methods you can actually use. So let's look at an example here. Let's say I want to find out E is prime, and I'm going to ask for, let's say, 1 and a few values, let's say 1, 2, and these could be a little sample to work with. So I want to find if any of these numbers, each of these numbers are prime. So we could say, for example, in this case, Boolean, and we could say E is prime, int number, and then, of course, in this case, we could determine if the number is prime. So what do? I could say Boolean, and we could say divisible is equal to, let's say, false. Well, it is not divisible, so we can say false over here. And then, of course, what we would do then is we could say for int I is equal to 2, I less than number. And then we could go through each one of the numbers, and we could say if number mod I is equal to 0, meaning it's divisible, then we could say divisible equals true, and then we would break out of it. Well, once we do, we can say if number is greater than 1 and not divisible, so this is going to be just a return of it. So return number is greater than 1 and we could say, for example, not divisible, and that's basically what we're going to return from this particular call. So essentially what we are doing in this code is we have taken the effort to do every single step in our code to really do the work all by ourselves, and that can become really, really tiresome. So this is a good way of thinking about imperative code where you do have to do all the work. Well, thankfully, we don't have to go through that much effort. What we can do instead is we can simply say, well, let's bring in a stream.star. Well, in this case, all we want to do is look for divisibility. So we can say return number greater than 1 and then, of course, we can say, in this case, int stream dot range. Well, we want to start with the 2. After all, that's the initial value. We want to go up till a number, but then I'm going to simply say dot none match the property of divisibility. So we can say number mod I is equal to 0. So you can see we transform that into a functional style rather than keeping it as an imperative style itself, and that becomes a lot easier to work with. So given this particular case, you can see rather than being in the business of looping, we can instead focus on simply expressing our ideas at a very high level. Which means when we start programming in functional style, rather than typing really fast, we got to slow down and rethink the problem, and then we have to go around and say, are there better ways to do this? Are there library functions available that I can use to get the work done? So you think a little bit more, and you write a lot less going forward in functional style of programming. Now, there's one problem, though. Most of us have been programming in imperative style for a very, very, very long time, right? And this is what we are used to. And now we have to start thinking in functional style, and that takes quite an effort moving forward. So, in other words, when a problem is given to you, you have to step back and say, rather than imperatively going through and figuring out how to do all these details, can I think of this as steps to take, and now can I look for functions I can use? Well, that takes a bit of time to do. I would say, personally, I am about maybe 50 to 60% there. So given a problem, maybe within minutes I can think in a functional style, but for some problems it may take a little longer, maybe an hour or two sometimes, and that's okay. Get it implemented imperatively and come back and make it better. After all, you want to make it work and make it better. So as time goes on, you can get better at writing code in a functional style and invest the time to really think functionally. So some of the core things to keep in mind. avoid mutability as much as you can, and try to write functions as pure functions as much as you can. When it comes to a problem, rather than trying to express the problem in ways of taking on the responsibility to do every single step and trying to not do every single how, instead focus on what to do and then come back and try to express that in code using functions, higher level of abstraction. One of the benefits you get at this point is when you work with programmers and business analysts and other people, rather than having to go and decipher what the code is doing, it becomes a lot easier to reason with the code and say, that's what the code is doing. So it becomes easy to find out what the code is doing by just talking over through it in a single pass, rather than looping through and trying to decipher what these variables mean. You also notice that the code ends up having fewer garbage variables. The variable like divisible or garbage variables, you don't have those in the bottom because you have abstracted out and you're saying, I'll tell you what to do. I don't have to go into the details of how to do it. That's left under the hood, and your programming works a lot better to write with this. So it's a lot of fun to be programming in functional style, but it does take a certain amount of effort for us to rethink functionally, but we will only get better with it as we do it. So anytime you have a problem on hand, find out, implement it if you want to in imperative style, have a sufficient number of tests around it, and then start refactoring to go to functional style. And the more you start doing it, you become really begin to think in a functional style. And since most of the languages are moving towards that way, and for all the benefits we talked about, that's a very logical step for us to move forward in that direction, and I hope you will be able to. Thank you.